the 146th birth anniversary of Marie Curie and the 125th birth anniversary of Sir C. Taboo, the reason for which we are celebrating this week long away. As a part of celebrations today, we have with us Professor K.L.Sebastian from the IISc Bangalore. Professor Sebastian did his bachelor's from Kerala University and his master's in physical chemistry from Taboo University. He did his PhD from the Indian Institute of Science, Bangalore. He is a recipient of many awards, including the SS Award and the Linus Pauling Lecture Award, and has been a JC Bose Fellow since 2008. His research is about chemical phenomena using quantum and statistical mechanics. Today he will be talking to us about the energy transfer to nanoparticles, nanotubes, and graphene. Let's welcome him.
Thank you very much for the introduction. I do not know if she wrote all this material. I am very delighted to be here in the Curie Club in IISER Mohali, which is actually my first visit to IISER Mohali. And I thank the Curie Club and of course the Department of Chemistry, Prof. Raman, and the others who have been responsible for this research.
So just can you check? Is it audible? Audible?
Okay.
Oh.
I think it's working.
No.
So, well, unfortunately, I got include any slide about our institute, but of course, these days, the availability of web, you can see pictures of the institute. I don't have to show you. Except, so therefore, the only thing that I can say regarding the institute is this: so this picture was taken in the institute, right in front of the house where we used to stay. This was our garden. Okay. I wish I had included some slides. But a few words about my department. This is Department of Inorganic and Physical Chemistry. We have other departments. We have Organic Chemistry, we have Chemistry and Structural Chemistry, Materials, and so on. In fact, we claim to be one of the oldest in the campus. The department is 104 years, 102, 103 years old. It was established in 2009. Okay, I think that's all that I would say about the institute and my department. I am going to speak about resonance energy transfer. Fluorescence resonance energy transfer is usually referred to as FRET, cohesiveness. This is going to be energy transfer between two systems. I excite one system, energy is transferred to the other, and there is a distance between these two. And that distance I shall denote by this word capital R. And if you think of the rate of energy transfer, it decreases as you increase the distance, and the decrease goes like distance to the power of minus. These are two molecules, for example. You think of two molecules, you excite one, energy is transferred to the other. It's excitation. Everybody sees more details of this. So the question is why. I shall explain to you why it is so. Then I shall answer this question. And we have other dependencies. You may ask, why do I want to have that? And also I shall explain. Specifically, we will think of systems of dye. I excite the dye, energy is transferred to the nanoparticle. Or maybe I excite the dye and think of energy transferred to graphene. Surely you are familiar with graphene. I shall also talk about some recent experiments. I shall also think about energy transfer to carbon nanotubes. And then, of course, summarize my conclusions. Of course, I should tell you that I'm a theoretician. I don't do any experiments. As I usually say, I only think of doing things. I don't actually do anything other than thinking. And of course, use the number. And again, number I don't use so extensively like many people, many theoreticians. So let me tell you this. This is actually what is referred as a green fluorescent protein, which would have been in the papers a few years ago because a Nobel Prize was given associated with them. What you do is you excite this green fluorescent protein with the laser light. You excite it at 488, this is electronic excitation. And then you see, of course, after it is electronically excited, it can decay back to the ground state. I mean, you will have to say, okay, energy is given out somehow, energy may go to the surroundings as heat or something, or it is possible that the molecule may emit, right, the energy back to space. So that is the process of the fluorescence. So if you excite at 488 nanometers, then what you find is that there is emission. The emission is having a longer wavelength because emitter is less than the excitation that you have provided. Okay. So it emits at 507 nanometers. There is also something called red fluorescent protein. You can excite it using light wavelength 556. You find that the emission is at 586